Yes, I'm recording now. Okay, so this is the problem here. I hope that you all can see it. And the question is on 15 points, as you can see. So it's not negligible. So indicate whether the below configuration of the magnetic field are possible or not. Just justify briefly. The arrows indicate the direction of the magnetic field, and the thick arrows indicate stronger magnetic field than thin arrows. Okay. So, is there anyone who would like to volunteer on? Let me check. Let me see.
The first two are possible.
The first is possible. Okay. Why was it possible? Wait. Why is it possible? You have to justify. Justify briefly. So,
if you draw.
Yes. Go ahead, Leah.
If you draw a loop, then you have one arrow going in and one going out of the same like magnitude or strength.
Okay, so let me try to see if I can. If I draw this loop like this.
No, you have to include a second arrow.
How will I use a second arrow with a loop? The loop is something like this, right?
Yeah, but like a bit below so that one is going in and one is out.
Well, here one is coming in, one is coming out here.
قصد loop بقلبها 2 arrows اللي يبين انه same magnitude.
هيك.
No, in between those two loops.
Like this. Like this.
Yeah.
This one?
Kind of, yeah.
The last one? Okay.
No, the smaller one. Okay, yeah.
The smaller one? So which one? Go back, tell me. You want to have two arrows. Is this correct? Like this? This is coming in, this is coming out.
Yeah.
But this is going, yeah, this is the same as this one. This is the same. This is coming in and this is coming out. It's just indication. There's not one loop. There's a magnetic field. I'm representing this magnetic field with these arrows. You understand my point? So so this loop is exactly as this loop, and is exactly as any loop. You know what I mean?
Yeah, as long as there is one coming in and out.
Yes. There's not one magnetic field coming in represented by this arrow, right?
Yeah.
So guys, anyone can suggest anything? So Leah is suggesting that we put a loop. أحمد جرادي وينك يا أحمد؟ وعاء أحمد جرادي. Okay, جانا هارون.
نحن جبنا سيرة الدايفرجنس معك بس قليل يمكن.
احنا قلنا بلال احنا قلنا we have two ways of representing the Gauss's law for magnetism. Okay, one, the integral way is the integral over a Gaussian surface of B scalar dA that should be always equal to 0. Okay, and the other one is the same thing as divergence of B is equal to 0. So my question that Leah is suggesting a loop. So Leah, what would you write in terms of justification?
That the flux would be 0 because you have the same.
The loop?
Yeah.
Because you have the same thing coming as getting out, right?
Yeah.
Okay, I want to heed Jawad Hamayed.
Yes, doctor.
Jawad, wake up, my man. Do you agree with Leah?
Yes, it makes sense since the same arrows coming in are coming out.
Okay. Petra Georgis.
Yes, Professor.
Do you agree with Leah? You can unmute yourself.
Professor,
You can unmute yourselves. This is an open discussion.
I have a question here. It's like, isn't this the magnetic field created by a wire centered at like
Yes, but
the arrows?
that's right. Yes, this is absolutely true. But you have to justify. You cannot just tell me that this is created by a wire. It has to be related to Gauss's law.
Okay.
So do you agree with Leah that she drew a circle and the flux in is equal to the flux out?
Yes.
Yes, okay. شربل الأم مدري شو. شربل wake up يا شربل. If you don't ask these questions, then it's never going to happen. Sharbel.
Professor,
Yes, Tamar.
question. Are we proving the existence of the magnetic field?
Yes.
This is the
in
question.
Tamar, in some way, yes. Okay. In some way, when I say that if these things can exist or not, in some way, it is as if you're proving their existence. You know what I mean?
Okay. Yeah.
So, Tamar, do you agree with Leah about her her idea?
Yeah, so we're using Gauss's law to prove the existence. Yes, I think this is a good way.
Okay. طيب يا تمام. Or maybe أحمد علاء لا علاء مكاوي علاء مكاوي. Are you here? علاء؟ علاء من هو؟ طيب عمر غليني كمان منه ما حدا هون فيني عرفت شو بيجيبوا كمبيوتر بيجيبوا their phone, they open the meeting and then they go away.
كان بيعمل قهوة.
ايه بكون عم يعمل exactly عامل ارجيلي هلا الصبح مثلا. Okay, Leah, let's go back to you, Leah. Leah, you have all the people are with you. Leah, can you hear me?
Yeah.
Okay, it seems like you have strong, a lot of people are with you, except me, of course. طيب يا Leah, let's see, what is Gauss's law? What does it say, Gauss's law?
The integral of BdA
Integral of
equals 0 of a closed surface.
Did you just draw a closed surface? So right, a Gaussian surface, okay, of B scalar dA, that's equal to 0. So my question to you, Leah, is your circle that we just drew here, is this a closed surface?
Yeah.
Yeah. It's
No.
I can make it bigger as small as much as I want. So I'm going to write here the problem with Leah's suggestion is that a circle or a disk, a disk is not a closed surface. Do you remember how to make a closed surface?
You can use a cylinder.
You can use a cylinder, but in your mind, how do you imagine a closed surface? Michel Modi.
Yes, sir.
How do you imagine a closed surface, Michel?
Like a sphere.
Okay. Other than a sphere.
Instead of a disk.
How would you imagine other? I mean, can you give us a general rule of imagining a cylinder? A cylinder could be close. The idea, Leah, is that a closed, I'm going down, a closed surface is a surface which englobes an object. So first, you can imagine an object. It could be a sphere, it could be a cube, it could be a cylinder, and then the whole surface around it is the closed surface. Okay, Leah?
Okay.
Okay, so consequently, the problem is not a closed surface, but you can imagine something which is similar to that. So instead of having this, what you can imagine is another, let's say, another one like this. That's my cylinder. Okay. Now I can say that the flux, wherever I choose my cylinder, the flux going in is equal to the flux going out. عم تسمعوني يا جماعة؟
Yes, we are hearing you.
Yes, yes.
Okay. So, and this is the case if I choose my cylinder here. Also, this is 1, this is 2, this is my cylinder. Okay. And so in this case here, I have the flux going in is exactly equal to the flux going out. Okay. But this
Which is not applied in the third one, right?
exactly. Here, if I choose
Because we have stronger magnetic field.
exactly. So we have stronger magnetic field on the right-hand side than on the left-hand side. For this reason, this net flux is not equal to 0, and this magnetic field cannot exist. And so this goes back to Tamas' remark, is that are we choosing that the existence of these magnetic fields? Yes, we are choosing the existence of these magnetic fields. And we can say that the first two, they can exist in nature, but not the third one. Okay? And
Sir, Gauss's law applies. Sorry.
Yeah, go ahead, Bilal.
Gauss's law applies to even electric fields with non-constant E.
Which Gauss's law? This is for magnetism. This is not for electricity, Bilal.
Hey.
For electricity, you cannot write equal to 0.
You cannot show ما سمعت.
ما فهمت السؤال تبعك مظبوط.
نحن لما كنا نطبق جاوس's law على الالكتريسيتي كنا نعمل الانتجرال بتاع E over كذا equal
charge inside
Q over
مظبوط.
بالماجنتيزم ما مش نفس الشيء.
لا
شو الفرق؟
Q بدك تقول انت BDA equal to 0. لأنه you cannot have a net charge, a net magnetic charge. There are no monopoles.
اوكي.
فهمت علي؟ يعني if I have a plus charge, I always have a negative charge. ليه؟ لأنه if I have a north pole, I always have a south pole.
اوكي انا يعني اذا بنعتبر هذا electric field it can exist بس كمagnetic field it can't.
Yes, of course.
Okay.
Of course. And here we're talking about the magnetic field.
Sir, how can we write the answer for this question?
Yeah, so basically, exactly, integral Gauss's law, I would state, Gauss's law, I would write Gauss's law states, okay, integral of BDA is equal to this one. In this case, I'm going to say, I'm going to choose, let the Gaussian surface be a cylinder. If you want, as shown, as drawn in the figure. Okay. The point that the amount of field lines going into the Gaussian surface is equal to the amount of field lines going out. Consequently, this magnetic field can exist. The same applies for the second picture. The third picture indicates that the magnetic field, the magnetic flux for a cylinder going into the cylinder, sorry, going into the cylinder, which is our Gaussian Gaussian surface, is greater than the magnetic field, magnetic flux, sorry, getting out. Therefore, it cannot exist. Oh, wait. Wait a second. I'm sorry about guys, but this is a bit weird. But you get the point. Did you get what I wrote? Yes.
Yes, thank you.
Yes, sir. Yes.
Okay, let's move on. But I need to get rid of, ya Allah. I need to get rid of these guys. Otherwise, they will remain with us. Okay, so the idea here, the trick is the choice of the Gaussian surface. You know, the fact that you choose it to be a closed surface. That's the trick in the problem. Okay? Okay. Let me go back to the other one. Wait a second. Okay, so this is done. Now we continue here, okay? So let's start from here. Briefly, now, number 2, use to illustrate the direction of the magnetic field lines. We said that in order to do the magnetic field lines, first you draw R, which is the vector from the source to the point in space. Okay, so for example, this is going to be how did I do it? Let me see. Okay, this is going to be, this is my R from source 2, and then my my B will be perpendicular to it like this. Okay, so I into out of the page as shown here in the figure. So it's towards me. R is downward, and then B is this direction. So that's how I get my magnetic field. Sorry. Okay, so I hope this, and then the second from 1. Okay, from 1 I can have, this is my R, and that's my B. Okay, I hope this is clear for everyone. Okay, now determine the magnetic field the magnetic field for I that flows along the wire 1 shown in the class. So basically, then I go back to wire 1. This is my wire 1. How do I determine magnetic field? I must, of course, use our friend Mr. Ampere. Okay? That's the idea. The idea is to use Ampere's law and notate. So here we're going to say so we use Ampere's law, which states integral over Amperian loop, right, of B scalar dl equal mu 0 in. That's the idea, okay? Then the next step is to choose the Amperian loop. So this is for just one wire, okay? One wire. We have done this in class. So first we say the Amperian loop. The Amperian loop is a circle centered on the wire with radius r. Now, you know, with radius r, yes. Now we can start integrate. So integral over circle, if you want, the circle of B scalar dl, B scalar dl, dl a cosine theta. I'm going to put it like this, cosine theta. Okay, this is equal to integral over the circle of BDL, in parentheses, theta is always equal to 0, okay, on the circle. Okay, now the other issue, since B is at the same distance from the wire, okay, then we assume that B is constant at the distance R, or on the circle at R. Okay, so this gives me integral of the Amperian loop of B scalar dl is equal to B integral over the circle, which is equal to B multiplied by 2 pi r. So that's the integral part. Now what's my IN? My IN is equal to I, since the circle intercepts the wire 1, okay, the whole wire 1, the whole wire 1. If we were asked to determine the magnetic field inside, okay, in this case it does not intercept the whole wire 1. That's IN cannot be is not equal to I, but equal to some part of I, and that's where we use J, which is equal to I. Okay, so this is putting things together. Then I'm going to have B is equal to mu 0 I divided by 2 pi r. That's the magnetic.
Sir, can you repeat what do we do if the I isn't included in the circle?
We have done this before. If I is not, if I have a let's say a wire, and I'm asking to calculate the magnetic field inside. Okay, and this,
Sir,
your Amperian loop, yes.
we use J, right? If the
Exactly.
not all the I is included.
Exactly. Now we're gonna be cut in less than a minute. We'll continue. Okay, immediately. After, yes. So basically, we use J equal to I over A or IN divided by the area of the circle that you have chosen. Okay, Bilal?
Okay.
I think, yeah. Okay, so this is the, that's the problem now. And then we're going to continue in the X direction and the Y direction, but just after this.